In this video, I will talk about biased clipper circuit, specifically biased positive clipper circuit. So what is a biased clipper circuit? The biased clipper circuit is required to remove a small portion from the positive or negative half cycle of the applied input voltage. During the analysis of positive clipper circuit, I have shown you that in the positive clipper circuit, it will remove the positive half cycle of the applied input voltage and gives only the negative half cycle in the output side, and in the negative clipper circuit it will remove the negative half cycle and gives only the positive half cycle in the output. But a biased clipper circuit is such that it will remove a small portion of the positive, or it will remove a small portion from the negative half cycle of the input voltage. Therefore that will be our biased clipper circuit. Now how the biased clipper circuit forms? We know that a clipper circuit must contain at least a diode and a resistor, and if we add an additional voltage source in the basic clipper circuit, that circuit will be our biased clipper circuit. At first I will talk about positive series clipper with bias, that means biased positive series clipper circuit. When a diode and a resistor is connected like this, that is known as positive series clipper circuit, and if I add an additional bias voltage or a voltage source of plus VR, that will be our positive series clipper with bias, or biased positive clipper series clipper circuit. Here our reference voltage is plus VR, therefore this is our biased positive series clipper with positive bias. And if our bias voltage is connected like this, that means we are applying minus VR here, then that will be known as biased positive series clipper with negative bias. At first I will talk about bias series clipper with bias. When we have to analyze a circuit with a bias voltage VR, we have to at first we have to indicate the transition voltage in the input. Transition voltage, that means in one side of it the diode will be on and another side the diode will be off. So at first let me indicate our transition voltage. See, when the input voltage is at negative half cycle, that means from this point to this point, this terminal will be negative and this terminal will be positive. At first I will analyze. Now see, here we have two voltage source connected with this diode. First one is that this input voltage, and second one is this reference voltage, and we will at first try to see the effect of the voltage source individually in this diode. So if I consider this input voltage, the positive terminal of the input voltage is connected with the P side of the diode, and the negative terminal of the diode is connected in the inside of the diode. That means this input voltage will drive the diode is in forward bias. Now consider this reference voltage. See, in case of this reference voltage, the positive terminal is also connected with the P side and the negative terminal is connected with the inside of the diode. That means both this input voltage and this reference voltage are trying to drive the diode in forward bias. So during the entire negative half cycle, our diode will be in forward bias. Therefore I can conclude that our transition voltage will be in the positive half cycle. See, during the positive half cycle of the input voltage, this terminal will be positive and this terminal will be negative. Now consider the effect of individual voltage source in case of this diode. If I consider this input voltage, this terminal will be positive and this terminal will be negative. That means this input voltage is trying to drive the diode in reverse bias. Now consider the effect of the reference voltage. The positive terminal is connected with the P side and the negative terminal is connected with the inside of the diode, and in case of input voltage, positive terminal, negative terminal is connected with the p side, and the positive terminal is connected with the n side. Okay, so what is this transition voltage? The transition voltage is that amount of input voltage for which the effect of this input voltage and the effect of this reference voltage will be equal to 0. That means here the input voltage is trying to drive the diode in reverse bias, and this reference voltage is trying to drive the diode in forward bias. Therefore, when this input voltage has a value of Vi equal to Vr, when the input voltage is equal to the reference voltage, the combined effect or the resultant effect of this input voltage and the reference voltage will be equal to 0, and that voltage will be our transition voltage for this circuit. So this is our transition voltage TV, and when the input voltage Vi is greater than this transition voltage, our diode will be off, and when the input voltage is less than the transition voltage, our diode will be on. Now consider the input voltage is greater than the transition voltage. That means the diode will be in reverse bias, so the diode will be in off state. That means I can as the diode is in reverse bias, I can replace this diode with an open circuit. If I replace the diode with an open circuit, the current that is flowing in the circuit I will be equal to 0. Therefore, the voltage drop across this resistor equal to IR will be equal to 0 volt. That means for the input voltage from this point to for the input voltage within this interval, that means when the input voltage is greater than the transition voltage, our output voltage will be equal to plus Vr. Our output voltage will be equal to plus Vr, which I can show in the output waveform like this. From this point to this point, the input voltage is greater than the transition voltage and our diode is in off state, so our output voltage will be equal to plus Vr. Now consider this portion of the input voltage. When the input voltage is less than our transition voltage, in that case this diode will be in forward bias. Therefore, I can replace this diode with a short circuit. So if I replace this diode with a short circuit, I will see that the applied input voltage will be appeared across these two terminal, and we are taking the output voltage across these two terminals. So our output voltage will be equal to input voltage. That means the output voltage will be changing in the same way as our input voltage is changing. So from this point to this point, input voltage is changing like this. So I can show this in the output waveform like this. From this point to this point, input is changing like this, and from this point to this point, the input voltage is going through negative half cycle. So our output voltage will go through negative half cycle, and this is our output voltage for this biased positive series clipper with positive bias voltage. Now let me show you biased positive series clipper with negative bias. Our applied input voltage will be negative. See here, the negative terminal of the bias voltage is in upward direction, and the positive terminal of the bias voltage is in downward direction. So this is a negative bias circuit. During the positive half cycle of this input voltage, this terminal will be positive, this terminal will be negative. See, the positive terminal is connected with the N side and the negative terminal is connected with the P side in case of this input voltage, and also the negative terminal of the reference voltage is connected with the N side and the positive terminal is connected with the P side. That means during the positive half cycle, both the input voltage and the reference voltage are trying to keep the diode in reverse bias. Now let me consider the negative half cycle. During the negative half cycle, this terminal will be negative and this terminal will be positive. So this positive terminal will try to drive the diode in forward bias, and the negative terminal. So during the negative half cycle, the input voltage will try to will try to drive the diode in forward bias. Now consider the effect of this reference voltage. The negative terminal is connected with the P side and the positive terminal is connected with the N side. So this reference voltage is trying to drive the diode in reverse bias. So at first I have to indicate the transition voltage. So now I have to indicate the transition voltage in the input voltage for which the diode will drive in forward bias. See, when the value of this input voltage is exactly equal to this negative reference voltage, the resultant effect of this input voltage and the reference voltage will be equal to 0 in case of this diode. This will be our transition, so this voltage will be our transition voltage. Below, when the input voltage is less than this transition voltage, our diode will be on or in forward bias, and when the input voltage is greater than this transition voltage, our diode will be off or reverse bias. When the input voltage is greater than our transition voltage, this diode is in reverse bias or in off state. So I can replace this diode with an open circuit. If I replace this diode with an open circuit, our circuit will look like this, and the current in this circuit will be equal to I, or current in this circuit will be equal to 0. As there is no current in this circuit, our voltage drop across this resistor IR will be equal to 0. Therefore our output voltage will be equal to minus VR, because see, here the positive terminal is connected here and the negative terminal is connected here, and we are taking the output positive, we are considering the positive terminal of the output at this terminal and the negative terminal of the output at this terminal. So our output voltage will be equal to minus VR from this point to this point, which I can show like this. Within this interval, our output voltage will be equal to minus VR. Now consider this interval from this point to this point. When the input voltage is less than the transition voltage, in that case this diode will be in forward bias, so I can replace this diode with a short circuit. If I replace the diode with a short circuit, our new circuit will look like this. And see here, during this interval, that when the input voltage is less than the transition voltage, our applied input voltage will be appeared across the output terminal. So when the input voltage is less than the transition voltage, our output voltage will be equal to our input voltage. That means from this point to this point, our output voltage will follow the same shape as our input waveform. Okay, so our input will look like this, and after that our output voltage will be equal to minus VR, which will be like this. So this is our complete waveform in case of this biased positive series clipper with negative bias. Now I will show you the operation of biased positive shunt clipper, one with positive reference voltage and another with negative reference voltage. See, here we have a resistor and the diode, and this is the positive shunt clipper circuit, and if we add a bias voltage VR, then that circuit will be biased positive shunt clipper circuit. Let's say I am applying a sinusoidal voltage in the input side, and this sinusoidal voltage has two half cycle, positive half cycle and a negative half cycle. So when we apply a reference or bias voltage, in that case at first we have to identify the value of transition voltage and the region in which the diode will be in forward bias and the region in which the diode will be in reverse bias. So let me consider the positive half cycle of the input voltage. This terminal will be positive and this terminal will be negative. See, the positive terminal of the input voltage is connected with the P side of the diode, and the negative terminal is connected with the N side of the diode, and so this input voltage will try to drive the diode in forward bias. And if I consider the effect of this reference voltage, the positive terminal of the reference voltage is connected with the N side and the negative terminal is connected with the P side. That means this reference voltage will try to drive the diode in reverse bias. We have to derive the condition in which the resultant effect of this reference voltage and this input voltage will be equal to 0, and that voltage will be our transition voltage. See here, if the input voltage is equal to VR, then it will minimize the effect of this reference voltage. So I can say that Vi equal to plus VR will be our desired transition voltage. Now see, the value of input voltage above this transition voltage will drive the diode in forward bias. So in this region diode will be on, and the value of the input voltage below this transition voltage, our diode will be in off state or in reverse bias. Here the diode will be in forward bias. So consider the input voltage above the transition voltage. This diode will be in forward bias, so I can replace this diode with a short circuit. If I replace this diode with a short circuit, our new circuit will look like this circuit. See here, as long as the input voltage from this point to this point, the input voltage Vi is greater than this transition voltage, in that case our output voltage will be equal to plus VR, which I can show from this point to this point our input voltage is greater than the transition voltage. So in this interval our output voltage will be equal to plus VR. So now consider the value of the input voltages below this transition voltage. So input voltage is less than the transition voltage. That means this diode will be in reverse bias. So when this diode is in reverse bias, I can replace this diode with an open circuit. So when this circuit gets opened, the current in the circuit will be equal to 0. As the current in the circuit is 0, the voltage drop across this resistor IR will be equal to 0. That means for the input voltage, that means in case of the input voltage less than this transition voltage, our output voltage will be exactly equal to our input voltage. That means our output voltage will follow the same waveform as the input voltage. So from this point to this point, input voltage is changing in this way, so our output voltage will be like this. From this point to this point, our input voltage is changing this way, so our output voltage will also follow the same shape. From this point to this point, our input voltage is going through negative half cycle, so our output voltage will also follow the same wave shape, and this has a negative maximum of minus Vm, and this will be the output of the negative shunt clipper bias circuit with positive bias. Now consider the biased positive shunt clipper circuit with negative bias. See here, the applied reference voltage is in downward direction. Here the positive terminal is in downward direction and the negative terminal is in upward direction. So this is a biased positive shunt clipper circuit with negative bias. This is, we are taking the output across these two terminals. This is the positive terminal of the output and this is the negative terminal of the output, and I am applying the same sinusoidal signal in this circuit. This is our positive half cycle and this is our negative half cycle. As we are applying a bias voltage, that means at first we have to indicate the region in which the diode will be in forward bias and in which the diode will be in reverse bias. So during the positive half cycle, this terminal will be positive, this terminal will be negative. As this terminal is positive terminal will be connected with the P side of the diode and the negative terminal is connected with the N side of the diode. Okay, and in case of this, so this input voltage is trying to drive the diode in forward bias, and the reference voltage, the negative terminal of the reference voltage is connected with the N side of the diode and the positive terminal is connected with the P side of the diode. If I consider like this, then that means that during the positive half cycle of the input voltage, both VR and Vi are trying to drive the diode in forward bias. That means during the positive half cycle, the diode will be in forward bias. Now consider the negative half cycle. During negative half cycle, this terminal will be negative and this terminal will be positive. See, the negative terminal is connected with the p side of the diode, and the positive terminal is connected with the n side of the diode. So the input now, during the negative half cycle, the input voltage is trying to drive the diode in reverse bias, and in case of the reference voltage, input is the negative terminal of the reference voltage is connected with the n side, and the positive terminal is connected with the p side of the diode. That means the value of input voltage has to be equal to this minus VR, and when this input voltage is equal to minus VR, that will be the transition voltage in the input waveform. So when Vi equal to minus VR, that will be our reference, and this is our transition voltage. And above, for any value of the input voltage above this transition voltage, our diode will be in forward bias. That means diode is in on state, and any value of the input voltage, our input diode will be in off state or in reverse bias. Okay, now consider the value of input voltage greater than this transition voltage. In that case, our diode will be in forward bias. So we can replace this diode with a short circuit. If I replace the diode with a short circuit, our circuit will look like this, and you will see that we are taking the output across this terminal and this terminal, and you will see that a reference voltage and its negative minus VR is connected in parallel with the output terminal. That means that as long as the input voltage is greater than the transition voltage, from this point to this point, our input voltage is greater than the transition voltage, our output voltage will be equal to minus VR, which I can show like this, and this level will be equal to minus VR. Now consider the value of input voltage less than the transition voltage. That means the voltage values lying between this point to this point. Here the input voltage is less than this transition or minus VR voltage. So in that case, this diode will be in reverse bias. So I can replace this diode with an open circuit. So when the diode is in reverse bias, I can replace that diode with an open circuit as if the diode branch does not exist in the circuit. So if this is an open circuit, our current flow in the circuit I will be equal to 0. As the current becomes 0, therefore the voltage drop will be also equal to 0. That means the applied input voltage will be appear directly across the output, and during this interval, that means from this point to this point, our output voltage will follow the same shape as the input is going through. So our output voltage will like this, and with a negative maximum value of minus Vm. So this is the complete output voltage waveform of our bias positive shunt clipper with negative bias, and this ends my lecture regarding biased positive clipper circuit. Okay, that's it.